In this episode, the most audacious rail tunnel ever built.
The Gotthard Base Tunnel is the longest railway tunnel in the world, 57 kilometers long.
Slicing through the heart of a mountain range.
We go in tunneling quite blind because nobody has been there before.
And the pioneering historic innovations.
Let's get out of here. Now, this is a place that very few people get a chance to see.
That made the impossible possible. The Alps, the greatest mountain range in Europe. At its heart is Switzerland, whose alpine routes through the Gotthard Pass form the most crucial transport links across the continent. But Swiss engineers like Renzo Simoni are facing a seemingly impossible problem. In recent decades, traffic has increased tenfold, and the mountain passes are grinding to a halt.
Nowadays there are 1,200,000 lorries crossing the Swiss Alps every year, so we have to do something.
The Swiss solution? To bore a tunnel, the like of which the world has never seen.
This is the biggest and most complex and of course most expensive project Switzerland has ever done.
The Gotthard Base Tunnel will be 57 kilometers long and lie almost 2.5 kilometers below the mountain peaks. If Renzo and his fellow engineers can pull it off, it will be quite literally a groundbreaking engineering feat.
This is the longest railway tunnel we are building now here. It's 57 kilometers long, and that means it will be a world record.
But constructing a tunnel of this scale is far from straightforward.
We have many logistical problems. We have high overburden up to 2,500 meters. We have water which is coming inside the tunnel from time to time. We have the rock heat itself with temperatures up to 45 degrees. So there are a lot of challenges.
Since the dawn of time, mankind has felt the need to dig tunnels. Be it for shelter,
There's gold in them hill.
or to mine the Earth's resources. Enemies of the Romans used tunnels to attack them. But even Hannibal had to rely on elephants to make his way through the Alps. Before excavations of the Gotthard Base Tunnel can begin, engineers face their first seemingly impossible puzzle. How can they see through the solid rock in order to predict the potentially deadly hazards that lay ahead of them?
While tunneling, you have different dangers. It may occur that water comes in under high pressure, big amount of water, so that could be a problem. Or if you have a collapse of the front of the tunnel with material coming down.
Dirk Kruger from Amberg Technologies is a geophysicist facing the challenge.
The normal condition is that we go in tunneling quite blind because nobody has been there before. And the situation is very complex in the Alps. Geology can change from meter to meter.
The extreme depth of the tunnel rules out conventional surveying that takes samples from above. And being unable to predict the geological conditions ahead could be catastrophic.
So if you have a big water-bearing zone, this is the worst case because you have tons of water which are coming suddenly.
The solution to this perilous problem lies in one of history's great inventions. Japan is the most seismically active country on Earth, with roughly 1,500 quakes registered each year. For centuries, little was understood about their cause, nor where they may strike. That was until 1880, when, on a survey in Japan, British mining engineer John Milne experienced a severe quake and began to record their behaviour.
What I've created here is a simple demonstration of a seismograph. I've got a pen attached to a pendulum. When I shake the table and pull the paper through, you'll start to see the pen record the number of shakes on the paper, and that represents the frequency and the amplitude, or the number of times per second of the shakes and the size of those shakes. So, let's give it a try. My assistant Kirk here is going to come and shake the table, and as I pull the paper through, you can start to see the trace on the paper, and then if Kirk gives it a really big shake, you can see that increase in amplitude, and then as it calms down, it gets less again. And we can see here where the really big shake was compared to the rest of the time. It's a really simple but quite effective demonstration of how a seismograph works.
John Milne and a team of engineers took this very simple concept and enhanced it, devising the first continuously running seismographs which could detect the epicenter of the quakes in Japan. A design that was taken up and used all over the world. In order to see through solid rock, engineers building the Gotthard Tunnel will adapt Milne's innovation and make waves of their own.
Normally the seismographs are monitoring signals in Earth. Here the difference is we create a signal, a small earthquake, which creates waves which are traveling through the rock.
At the VSH Hagerbach Tunnel Research Facility, seismic prediction experiments are undertaken for the Gotthard project. Explosive charges are placed within the rock face. Once detonated, each sends out shockwaves which are measured.
This wave travels through the rock until some condition in the rock changes.
Distinct geological features reflect the waves differently, providing a picture of what lies ahead.
Everywhere where we find these lines, there is an area where we have changes in rock conditions. In water, they travel quite slow. In air, they're more slow. With this system, we are able to have a real impact on the tunneling progress.
Construction begins on history's most ambitious subterranean project in 1996. The route will consist of 2 tubes. And to reduce construction time, the work begins from 4 sites simultaneously, with the ultimate goal that the tunnels will join up underground. But in creating the world's longest and deepest subway, engineers will face many more challenges, and will have to draw on the innovators of the past.
Now this place is really incredible, really amazing.
To make the impossible possible. In the mountains of Switzerland, engineers are undertaking one of history's most audacious construction projects. A 57-kilometer rail tunnel driven straight through the Alps. It will be the longest and deepest ever built, and a feat once thought impossible
It's really a big innovation to do this. It's very, very tough. Sometimes it's like unbelievable that it's real.
Renzo Simoni is one of the team charged with turning the dream into reality. But they face a series of monumental engineering tests.
It's the longest tunnel ever built. We have, of course, very different geological zones to get through.
So how do you dig a tunnel that far without taking centuries to do it? It's a challenge that would have been impossible without history's great engineering innovators. London, England. Every day, 4 million people descend into a complex underground network of tunnels, more than 20 of which crisscross their way beneath the mighty River Thames. But it wasn't always so. By the early 19th century, Londoners had given up all hope of having a crossing beneath the river. As engineer Professor Luke Bisbee is investigating.
Several previous attempts to tunnel under the Thames had failed, and the problem was the soft and malleable London clay and sand. Hard rock miners had come from Cornwall, but the techniques that they used on hard rock had failed, leading to collapse and flooding. Eventually, it was decided that the project was impossible, and it was written off.
But Anglo-French engineer Marc Brunel, father of Isambard Kingdom Brunel, had a brainwave. As a naval cadet, Brunel had observed the perfect tunnel-like structures left by mollusks called shipworms as they burrowed through timber.
As it digs, this marine mollusk shoves pulped wood into its mouth and digests it. And its bivalve head and hard shell help support the creature as it moves through the wood. The pulp is then excreted as a hard, brittle residue that lines the rear space, creating a tunnel-like structure. The key is to not actually suck all the sand out of the tube. The mollusk then uses its back legs to grip itself to the side of the tunnel and push itself forward into the space that it's created, repeating the process until it finds light at the end of the tunnel. And this is exactly the process that Brunel sought to emulate.
Brunel's idea started an underground revolution, hidden remnants of which can still be found.
Now this place is really incredible, really amazing. Through a tiny door up at the street, down a rickety old scaffolding, and we find ourselves here in this cathedral-like space.
From this access shaft, Brunel drove the first ever tunnel under the Thames, using his engineering equivalent of the shipworm. A mobile steel framework called a tunnelling shield acted like the worm's hard head, supporting the earth and preventing collapse. Working in individual compartments, miners excavated just 4 inches before the whole tunnelling shield was pushed forward using screw jacks. A second group of men working behind them would be lining the tunnel with bricks to prevent its collapse. Finished in 1843, Brunel's Thames Tunnel was hailed as the 8th wonder of the world, with almost 50,000 visitors on opening day alone. Today, it forms part of the London Rail network, and it all began in this hidden chamber.
Most people would have no idea that it's here, but of course its importance to engineering and to tunnel engineering in particular really can't be overstated.
The Gotthard Tunnel will be more than 140 times longer than the Thames Tunnel, a feat that would be near impossible without Mark Brunel's innovation. In order to chew their way through the Alpine mountains, Renzo and his fellow Swiss engineers are using the modern supersized equivalent.
These machines are really very amazing. You have to imagine it's 400-meter long, the whole machine.
Almost the same length as the Thames Tunnel and weighing 300 tons, these tunnel boring machines, or TBMs, are some of the biggest land vehicles on Earth. So huge, they're shipped in sections and assembled on site.
This is the head which is rotating, and we have about 60 of those discs which are scraping the rock, so it advances like a worm in principle, step by step.
The head turns and breaks chips from the rock, each disc exerting a force of 32 tons. The excavated rock is passed back through the machine on a conveyor. The TBM is then pushed forward into the void on hydraulic legs.
20 years or 30 years ago, it would not have been imaginable.
These mechanical mollusks can munch through 40 meters of rock a day. Behind it, instead of Brunel's bricks, the walls are sprayed with shotcrete, a form of liquid concrete.
Shotcrete is the first safety measurement after excavation and is applied at the walls to assure that no pieces of rock is falling down. With this shotcrete lining, the tunnel is safe.
The giant TBMs carry all the equipment and materials required to bore and reinforce the tunnel. And automation undertakes many of the tasks that Brunel's bricklayers once did. All in all, they measure the length of 4 football pitches stretched end to end. Figuring out the direction to send these mighty machines is its own challenge. Calculating a straight route can be difficult enough on the surface of the Earth. There are trees, hills, and other obstructions to overcome. But it is possible to use landmarks to navigate, or build towers to get direct sightlines. Finding your way beneath the Earth where even the slightest miscalculation could result in disaster is surely impossible.
Getting the TBMs meeting in the middle, it's a very, very big challenge because we have so long distances.
The solution relies on one of the greatest innovations of the 20th century. In 1960, American Theodore Maiman built the world's first laser. Out of basic materials he bought from catalogues. Placing a small ruby within a photographer's flashbulb, he was able to excite atoms, causing them to emit light particles called photons. His creation would change the world, allowing highly accurate measurements to be made over great distances. Less than a decade after Maiman's prototype, lasers were bounced off reflectors on the surface of the Moon, so the Apollo 11 mission could accurately calculate its distance from Earth for the first time. In Switzerland, guiding the huge boring machines will only be possible with the help of lasers. First, GPS is used to map the entire route. But with no satellite signal below ground, Each TBM relies on a geodetic guidance system, using incredibly precise measurements to stay on track.
You are measuring the angles and the distances, and this is trigonometry.
A laser theodolite is attached to the tunnel wall and fires a beam at a target on the front of the TBM.
The laser pointer indicates the precise direction, so the commander of the machine always has the control, and he can choose very, very small correction.
But with 57 kilometers of mountain ahead of them, Renzo and the team won't always be able to rely on the massive TBMs.
Let's get out of here.
And will have to draw on more innovations from the past to make the impossible possible. In Switzerland, engineers are undertaking one of history's most audacious construction projects. To reduce alpine gridlock and pollution, they're attempting to build the longest and deepest rail tunnel in the world.
For Switzerland, it's very important to reduce the traffic by freight lorries crossing the Alps.
The Gotthard Base Tunnel will slice a 57-kilometer route not over the Alps, but straight under them.
With our tunnel project, we bring northern and southern part of Europe closer together.
Cutting-edge surveying guides the giant tunnel boring machines, or TBMs, through the mountainside. But digging a tunnel deeper than anyone has attempted before leaves Renzo Simoni and the engineering team facing another seemingly impossible challenge. One that the TBMs can't overcome.
You can use tunnel boring machines only in conditions where you have hard rock, which is not squeezing. If you have pressure on the machine, it wouldn't work anymore. That would be a problem. So you can use those machines only in very good rock conditions.
Squeezing occurs when the pressure of the mountainside combines with weaker rock types. In extreme cases, it can result in the tunnel closing up again after it's been bored.
Squeezing rock is like if you make a dough at home and then you put a finger on it and took the finger out, then it tries to close.
If the team use a tunnel boring machine in the squeezing rock zone, the consequences could be disastrous. The solution is to go back to basics, and a technique that would have been impossible without one of history's great innovators. Engineer Luke Bisbee is in Cornwall, on the southwest tip of Britain, exploring an area once critically dependent upon tunnelling.
So it's hard to believe that 200 years ago, underneath the sea, was the largest concentration of submarine tin and copper mines anywhere in the world. And it's been estimated that all told, there's between 50 and 60 kilometers of tunnels out there underneath the waves.
In the 19th century, this tiny county was the world's largest producer of copper and tin, the crucial materials of the Industrial Revolution.
More than 2,000 mines like this one would have dotted the county.
Cornish miners were considered the best in the world, and their expertise was sought in tunnelling projects all over the planet. But by today's standards, their methods were incredibly inefficient. Mostly, the Cornish tunnels were hewn from the rock by hand, the only alternative being primitive explosives.
So this is black powder. This is the world's first chemical explosive.
Better known as gunpowder, early miners would laboriously bore holes by hand in which to lay their charges.
I'm going to light the fuses, and then we should have more than a minute to head down the tunnel. right, okay, so let's see what's happened here. Keeping in mind that it would have taken a couple of hours to drill each of these holes by hand, to then put the black powder in and only move that amount of rock, despite a pretty big bang, is a bit disappointing, frankly.
It was not only relatively ineffective, but also dangerous.
The miners would come back thinking that the charge hadn't gone off. The charge would then detonate quite late, and the miners could be maimed or even killed, and in many cases they were.
The invention of a new, more powerful explosive proved even more perilous.
So what I have here is a jar of nitroglycerin, and it was first synthesized in 1847. And you can see just how volatile it is if I take a small drop and place it on this steel plate, and then I hit it with a hammer. So where black powder needs a heated charge in order to coax an explosion, nitroglycerin just needs a small tap. And of course, down a mine, that could spell disaster.
In 1867, it was Swedish explosives expert Alfred Nobel, spurred on by the death of his brother in a nitroglycerine accident, who finally managed to stabilize it and create an explosive that would change the world.
He realized that if he took nitroglycerin and mixed it with kieselguhr, which is a naturally occurring clay-like material, he would end up with dynamite. And you can see that it's quite loose but quite malleable, and it could be rolled to eventually form dynamite sticks.
Nobel's next challenge was mass production. How to safely handle the vast quantities of nitroglycerine needed to make the new dynamite. In Ardea, Scotland, he found a solution.
Nobel really favored this area because of its remoteness, and the sandy soil allowed him to shape the landscape around his factory to protect production workers from potential explosions. It also allowed him to build mounds such as these around us, and on top of these he could place his nitroglycerin production huts.
In each nitroglycerin hut, one man was in charge of monitoring the temperature and another mixed, sitting on a one-legged stool to ensure he kept his focus.
Its sensitivity to temperature and friction meant that nitroglycerin couldn't be safely pumped, and so it was set to trickle down from the huts to the factory, letting gravity do the work.
Once it reached the factory, it was mixed with the absorbent clay before being rolled into sticks of dynamite.
Nobel had created a product that was now so stable that it could be dropped on the ground or even thrown into fires without exploding.
The new dynamite, combined with the invention of pneumatic-powered rock drills, led to a much quicker and efficient form of tunneling called drill and blast.
All right, that's it. Let's get out of here.
And ushered in a new age of mining.
3, 2, 1, firing! Wow, so that was quite something. A lot of power in that one. So we can really see here the power of the dynamite as compared to the black powder. The dynamite has taken that entire mass of rock and thrown it sideways. You can see what a game changer this would have been for the miners working down here.
Wherever engineers at the Gotthard Base Tunnel encounter zones of squeezing rock, they revert to the tried and tested drill and blast methods pioneered in the 19th century. Only they give the technique a 21st century twist. Specially designed 60-ton drilling rigs, known as jumbos, make the task quicker than ever before.
They are very fast. They need some few hours to bore all the holes needed.
Each 3-meter-long arm has a powerful electro-hydraulic drill to bore holes for the explosives. As one arm drills, the operator lines up another ready to bore the next hole.
The boring jumbo, he's able to make different borings at once. In the past, you only had one and it was carried by man. Productivity of such a jumbo is much higher.
Unlike dynamite, modern emulsion explosives only become active when mixed together at the rock face, making it much safer than traditional drilling and blasting.
So this lorry, although it's carrying the explosive, it's not dangerous because for detonation you need the two compounds. In this lorry is only one compound now.
Each detonation takes 8 hours to prepare, making drilling and blasting much slower. But constructing the tunnel without it will be impossible.
The TBM is faster in good rock condition, but if rock conditions are not so good, you come through with this method. If you cannot do it with drilling and blasting, you can't do it at all.
2, 1, go!
Once the team have blasted their way through the obstacle of the squeezing rock, they still have to deal with the mountain's natural inclination to close the new tunnel back up. Tests are done to see if rigid steel arches will hold back the enormous pressure.
We saw that the steel began to deform. We knew immediately that we have to take some countermeasures because otherwise our tunnel would be closed completely.
With the success of the project in jeopardy, the answer lies in an historic innovation. In 1932, engineers Heinrich Toussaint and Egmont Heinzmann revolutionized the German coal mining industry when they invented the TH-yielding steel arch support. Capable of withstanding huge pressure without collapsing, their innovation made it possible to excavate deeper than ever before. Unlike a conventional rigid steel arch, the jointed concentric rings of their design change shape to accommodate the pressure of the rock, rather than totally resisting it.
It's not the steel itself which is deformable. It's the joint of the steel. All of these joints could move into each other 50 to 60 centimeters without collapsing.
The solution is to bore a tunnel with a wider circumference than is ultimately required. The yielding rings then allow just enough movement to prevent the supports from collapsing, while still resisting the pressure of squeezing rock enough to stop it from closing the tunnel completely. This simple engineering, inspired by the past, is solving a seemingly impossible problem that might otherwise turn the tunnel into an historic failure.
Without this kind of steel arches in the squeezing zone, we would not have been able to build it.
On the 15th of October 2010, after 14 years of digging, boring and blasting, the dream becomes a reality. A TBM crashes through the final few meters of rock, the two halves of the tunnel joining for the first time.
Breakthrough was a very special moment. The last parts of the rock came down and we could see the machine behind.
After excavating more than 114 kilometers of rock, thanks to the laser guidance system, the TBMs complete their monumental job with incredible accuracy.
In the end, they reached a result like this, 1 centimeter vertically and 8 centimeters horizontally, and this was a very, very big result.
With the digging done, a new team of engineers and technicians must now make the tunnel safe for the thousands of trains and passengers who will pass through. A huge challenge that will only be achieved by looking back to the innovators of the past.
Now, this is a place that very few people get a chance to see.
And learning some tragic lessons from history. Due to open in 2016, the Gotthard Base Tunnel in Switzerland is a true feat of underground engineering.
Breakthrough meant that we have created a world record because it's the longest railway tunnel now. It's amazing.
But the tunnel's monumental scale presents its engineers with one more seemingly insurmountable problem: how to keep the passengers travelling within it safe.
It was one of the biggest challenges to find a tunnel system which guaranteed safety.
With huge volumes of passengers and freight travelling at high speed through a confined space, under 2.5 kilometres of solid rock, accidents could be catastrophic.
I would say fire is the worst case inside the tunnel.
For Renzo and his team, memories of one of Europe's worst road disasters in another alpine tunnel are at the forefront of their minds. In 1999, a lorry caught fire halfway through the 11-kilometre-long Mont Blanc tunnel, linking France and Italy. The tunnel quickly filled with poisonous smoke as the blaze engulfed over 30 vehicles, in an inferno which raged for more than 2 days. Of the 39 people who lost their lives, most died from smoke inhalation. To ensure the Gotthard Base Tunnel will be one of the safest ever built, its engineers have taken inspiration from the innovations of the past. In the UK, a groundbreaking engineering project below Liverpool's River Mersey changed tunnel safety forever. Professor Luke Bisbee is experiencing it firsthand.
So this is the Queensway Tunnel. And when it opened, it was the biggest and longest underwater road tunnel in the world.
Opened in 1934, it took 1,700 men over 8 years to construct. But it's not the digging of this tunnel that makes it revolutionary.
About 30,000 cars travel through this tunnel every day. And even with modern exhaust systems, that's a lot of fumes. And the engineering innovation in this tunnel is what solved that.
By the early 20th century, while it was possible to build ever longer road tunnels, engineers now had to contend with toxic fumes from the cars using them. In 1930, the decision not to install ventilation until after the opening of Pittsburgh's Liberty Tunnel had left motorists overcome by noxious carbon monoxide. To keep poisonous fumes at bay, the builders of this Mersey tunnel turned to physiologist John Scott Haldane. Famous for introducing canaries into mines as an early warning of deadly gases, Haldane worked on a series of experiments.
And this is what they came up with. It was the world's largest ventilation system. And incredibly, this system is still in use today.
In each of the 6 huge ventilation towers, fresh air drawn in at roof level is pumped underneath the roadway before being blown into the tunnel through ducts along its sides. At the same time, exhaust fans draw toxic fumes out through holes in the roof. The George's Dock ventilation tower is home to 6 of the massive fans circulating air through the system.
This one right here is 8.5 meters in diameter. And incredibly, these are the original fans that were first installed down here almost 100 years ago.
Each one can move 100,000 cubic feet of air a minute, safely pumping exhaust fumes from the top of the 60-meter-high tower above.
Now, this is a place that very few people get a chance to see. I'm standing right at the bottom of one of the ventilation shafts.
The huge height of the tower ensures the air supply isn't contaminated by vehicle exhaust fumes from the street.
And it's said that the air down here is even cleaner than the air for the people walking around in the streets of Liverpool.
Once the largest bore ever drilled, the road deck actually forms only the top half of the original tunnel.
Most people, when they drive through the tunnel, they think they're at the bottom, but they're not. Actually, below them is this 2-story high space called Central Avenue.
Designed to house a tram line never built, it now serves as the main air supply duct, where air drawn from the tower is blown into the road deck above.
It's pretty amazing to think that there's this space like this down beneath the road deck. And I have to say, pretty cool to be down here.
With its revolutionary ventilation system, the Queensway Tunnel provided the blueprint for all tunnel design that came after it. The designers of the record-breaking Gotthard Base Tunnel have taken the systems pioneered under the River Mersey and brought them to new heights of sophistication. Electric trains will run through the tunnels so they won't have to contend with exhaust gases. But the potentially catastrophic effect of fire requires a cutting-edge solution.
First aim is that the train leaves the tunnel. If this is not possible, second aim is to get to the multifunction station.
In the event of a fire, trains will either be diverted out of the affected tunnel at 2 crossover points along the track, or directed to one of 2 emergency stations.
These 2 multifunction stations are very, very important for the safety of the overall system.
As a train approaches, the station's ventilation system will be activated remotely from the tunnel control center. Powerful 2.5 megawatt extractors above the track will suck toxic fumes out of the tunnel, releasing it at the surface through an 800-meter high exhaust shaft. As 0.5 megawatt inlet fans replace it with clean air.
The ventilation system can bring fresh air in the tunnel 250 cubic meters per second.
At each of the tunnel's portals, 6 40-kilowatt jet fans will raise the air pressure in the unaffected tunnel, keeping it free of smoke during the evacuation.
People who have to leave a train come here through the connecting gallery and into the other tunnel, which is not involved in an incident, and wait until a rescue train will come. This system is safer than the rest of the railway network in Switzerland. If you are here as a passenger using the tunnel, you are safer than outside.
Once complete, the Gotthard Base Tunnel will not only redefine the map of Europe, it will rewrite the rules of tunnel construction. It stands as a testament to the people, past and present, who helped design and build it.
This project will last for generation. It's a project of a generation for more than one generation.
By drawing on the innovations of the past, adapting, improving, and making groundbreaking innovations of their own, the engineers and designers of this incredible tunnel have succeeded in making the impossible possible.
Generations of engineers wouldn't have been able to do this. I am very lucky to have spent 20 years of my professional life together with this project. It's like a part of me.